Internet addresses. In the previous video, it was discussed how the internet is essentially a massive network of computers communicating data back and forth with one another. However, what we didn't discuss was how exactly do computers find each other? How does computer A know where to send that information to? The answer to that is internet addresses. Just like with regular postal mail, if I want to send mail to someone in Nebraska, I can't just toss the mail up into the air and hope it lands where I want it to land. I need to know the specific location of where I want the mail sent, and that location has to be formatted in a specific way. No different with internet addresses. So, as I just mentioned, postal addresses follow a specific format. We start with the country, and then from there on, it gets more and more specific or more and more local. We start with the country, then the city, state, and zip code, then the street address, and then most specific of all, the name of the entity or person we want to send the mail to. Every device on the internet has a unique internet address, just like every home or piece of property has a unique address. Data that gets sent over the internet has a to address and a from address, just like regular mail. Each address follows an agreed upon format, just like regular mail. And we call this address the Internet Protocol address, also known as the IP address. Suppose these 5 computers make up a small local network of computers, and each computer has a unique number. That number is that computer's local address within that small network. And then, like all other networks, this network has a router that connects them all together. That being said, as was discussed in the previous video, this first level router is not the only first level router in the entire massive internet. Thus, this router needs a number as well that is unique from all of the other first level routers in the entire internet. Likewise, the second level router, which is not the only second level router in the entire internet, the second level router will have a number of its own as well that's unique to all of the other second level routers in the internet. And it does not stop there. The third level router will also have a number that distinguishes it from all of the other third level routers in the massive internet. Now, where am I going with this? Suppose I want to find the address of that computer way in the far top left corner. How would I do that? How would I format it? Well, we start with the uppermost level router, the address of that router, which is 53, then a dot followed by the address of the next level router, the second level router, followed by a dot and the address of the next level router, the first level router, which was 97, then the address of the computer. Altogether, this forms the IP address of that individual computer in the top left corner. It should be noted that all 4 of these numbers could be any number between 0 and 255. That's because under this protocol, each local network can have up to 256 computers. And there are up to 256 first level routers, 256 second level routers, and 256 third level routers. Hence why 255 is the maximum number any one of these devices could have. Now, that being said, why 255? Is this number completely arbitrary? Well, it's not. Here's how the number was derived. We know that for any 1-bit binary number, that number can be either a 0 or a 1. Thus, the maximum 1-bit number, when converted to decimal, equals 1. The maximum 2-bit number, when converted to decimal, equals 3. The maximum 3-bit number, when converted to decimal, equals 7. The maximum 4-bit number, when converted to decimal, equals 15. The maximum 5-bit number, when converted to decimal, equals 31. The maximum 6-bit number, when converted to decimal, is 63. The maximum 7-bit number, when converted to decimal, is 127. And the maximum 8-bit number, when converted to decimal, is 255. Another way to look at all of this information is that The maximum 1-bit number is 2 to the power 1 minus 1. The maximum 2-bit number is equal to 2 to the power 2 minus 1. And the maximum 8-bit number equals 2 to the power 8 minus 1. In general, for any x-bit number, I don't care what integer it is, for any x-bit number, the minimum value is 0, and the maximum value is 2 to the power x minus 1, where once again, x is the number of bits. So, that being said, the reason why 255 is the maximum value for all 4 of these numbers is because 8 bits is used to represent all 4 of these numbers. Right? So when I write all 4 of these numbers in binary, this is how the IP address would look. 32 bits. We call this an IPv4 address, which stands for Internet Protocol version 4. Using this format, how many IPv4 addresses are there? Well, if we treat this entire address as one large 32-bit number, then the number of IPv4 addresses is 2 to the power 32 minus 1, which is approximately 4 billion different addresses. Is this enough in 2018? Well, in the 80s, when this protocol was first created, 4 billion was more than enough. And it was thought that 4 billion would be more than enough for a very, very long time. However, there was no way back then that we could have predicted the invention of smartphones and tablets and other devices such as that. These kind of technology has skyrocketed the number of computer devices around the globe far past what we could have ever expected. Hence why we now use IPv6 addresses, short for Internet Protocol version 6. This version of IP addresses uses 128 bits, thus meaning that the number of different IPv6 addresses equals 2 raised to the 128th power minus 1, which equals this long, ridiculous number. And as it currently stands, we have not yet come close to using up all of these addresses. That all being said, I wouldn't blame you if the thought of a single address being 128 bits long makes your head spin. But that's where hexadecimal becomes our friend. With hexadecimal, we would never have to write out all 128 bits. Rather, instead, we could write the hexadecimal counterpart. Remember, each hex digit counts as 4 binary digits. So rather than write out the entire 128-bit number, we could take each 4 binary digits and convert it to a hexadecimal number. Thus, our IPv6 addresses can be written as a 32-bit hexadecimal number rather than a 128-bit binary number.